So thank you all for coming, and thank you to the organizers for the invitation to speak. So my goal in about 25 minutes, I guess, is to both tell you kind of an outline of what I think is a new construction of universal star quantizations, but that's the sort of the I think, because it should probably be a refereed and everything. And then with any time I have at the end, I'll try to describe how one would come up with this construction from thinking about lattice field theories of a KSC type. And each of these is only one slide. So I'm very happy to kind of elaborate on any point that you would like me to elaborate upon. So the basic context for my problem is to come up with a universal star quantization for formal Poisson, I guess a Poisson formal manifold is the correct order of the words to say. A formal manifold, manifolds are something that makes sense over the real numbers, but formal manifolds make sense over any field of characteristic 0. So I'm going to only work over the rational numbers. And a formal manifold is just the completed symmetric algebra of a vector space. That's the definition of formal manifold. This is somewhere where you can do Taylor series, and you never have to worry about convergence issues. And then then a Poisson formal manifold should be a formal manifold with a Poisson structure. And if you scratch your head and think a moment, you realize that the data of a Poisson structure on a completed symmetric algebra is given by a whole bunch of Taylor coefficients. And since the Poisson structure should be a bivector, it's determined by what it does on linear functions. And so it's the data of a formal Poisson manifold is the data, how does this work? It's the data of a vector space along with a bunch of maps from 2 copies of the vector space to some symmetric copies of the vector space. And they have to satisfy some version of the Jacobi identity, which you can write graphically if you would like. So what I mean by this is that I'm drawing every map by kind of somebody with 2 inputs and a bunch of outputs. And I'm not very good at drawing shuffles with straight lines. So what I'd like you to do is kind of, for each of these, actually sort of average. This is just some numerical factor that averages over all the ways to shuffle those output strands. And exactly what the numerical factors are in my talk, well, it depends on what you mean by Taylor coefficients, whether you like to divide by n factorial somewhere. So just ignore the numerical coefficients. So that's the goal. So the goal is to take as input data a formal Poisson manifold and to produce deformation quantization of this, which is to say to produce an associative structure that depends on a formal parameter h bar and is an associative multiplication on the completed symmetric algebra. And then, so I'd like to add the request of doing that deformation problem. I'd like it to be kind of universal, meaning that there should just be universal polynomials in the derivatives of the Taylor, the derivatives of the Poisson bracket. And I'd like to ask that all of the kind of term by term, if you look at the star product, at the deformation you get, they should all be bidifferential operators. This is a problem that was solved in '98 by Kontsevich. It's a very famous problem. It was posed many decades ago. I think I have a new solution, which I think has some qualitative differences from his. But I'll tell you already, I haven't been able to do any detailed calculations to know how different they are. They agree to they agree to order h squared, and that's as far as I can compute. So my talk's going to be mostly in the language of properads. That's a scary word for most people. You might know what an operad is. A properad is, well, I won't give you a definition. A properad is the data that you need to make sense of pictures like this. It's some labels for vertices, and you can compose. And the important thing that the PR stands for, I have no idea why. I mean, I sort of know why it's PR. The important thing about properads is that there's sort of compositions for directed acyclic graphs. There's allowed to be genus, but I'm not going to allow you to have any sort of directed loops in your graphs. Those I'm going to disallow, and I'm only going to have connected graphs. So that's the only types of compositions that I'm going to have. Okay. So I want you to remember what a Poisson formal manifold is. By the way, you guys should all complain. it should be possible to have these slideshows one off from each other so that I could have the slide I just finished on that board and the slide I'm talking about now on this board. Anyway, so I want you to sort of keep in the back of your mind the idea of Poisson formal manifolds, but I'm going to tell you about a different properad that's actually closely related. This is a properad called open one-shifted commutative Frobenius. So open means non-unital. Frobenius means what I hope you think it means. Commutative means what I hope you think it means. And one-shifted means that my multiplication has degree -1 in cohomological degree. See, I should have told you everything I'm doing was with chain complexes. And then actually, OK, so I want, that minus sign is correct. Commutative, if you're off by degree 1, means anti-commutative. And then here are the axioms. So I do have a co-multiplication, I have a multiplication, I have a co-unit, but I don't have a unit. And so let's see, I should be co-unital, I should be co-associative, I should be associative, and I should have a Frobenius axiom. And everything else follows from commutativity. And then the world of properads by now has a well-developed theory by people like Vallette and Laudet and Merkelov and Hirsch and Millez for kind of cofibrant replacements. So I'm not actually going to work with open one-shifted Frobenius, but with a cofibrant replacement of it. And I'm not going to define it for you. You can read, well, I could, but I would run out of time. I'll say very briefly what the cofibrant replacement of there's a very, very general construction that says that for any kind of object that you might have, you can always do cofibrant replacement. And what you do, the sort of universal cofibrant replacement of something, you write down all graphs that you could imagine ever constructing. Graphs because I'm working, or DAGs, I guess, directed acyclic graphs, because that's the type of compositions I have. So you write down all directed acyclic graphs. You look at all ways of labeling every vertex of your directed acyclic graph with any composition of these. Those are the generators of the cofibrant replacement. And then there's some differential that's complicated and encodes all the rest of the structure that I've left out. So the cofibrant replacement tends to take some nice small thing and make it really, really big. Oh, yeah, so why do I care about one-shifted? Because I care about things like the homology of a circle, and the multiplication and homology of a circle drops degree by 1. Okay. So, so the sort of the heart of my construction is that this guy, you all know that the homology of a closed manifold is a Frobenius algebra, maybe with some funny signs and shifts. And so you could ask does that structure lift to the chain level? And the answer is no, because you can't lift things from homology to the chain level strictly. But the answer you hope to be yes for kind of cofibrant replacement structures, for sort of infinity, for weakened structures. So here's a version of that statement. The theorem is that H-Frob, the homotopy Frobenius algebra, acts at the chain level on the chains on R. I've spent the last couple of years thinking about the algebraic topology of the real line. I kid you not, there's interesting things there. And it acts in a slightly special way. It acts by, so the homotopy Frobenius, so when I say acts on R, I mean that the chains on R, and by chains, I mean rational cellular chains for the cell decomposition of R. And so by acts on, I mean that I can construct an algebra for the properad. I can construct a homotopy Frobenius algebra on that vector space, that DG vector space. And I can construct it in such a way that it's translation invariant, which you should always sort of hope for, and also some sort of not quite locality. So you think that intersection, like this should be something like an intersection theory for chains. And you'd really hope that intersection kind of is actually local. If I take two chains that are kind of far away and intersect them, that should be 0. I can't quite do that, but I can get some sort of quasi-locality. So for any piece of the homotopy Frobenius structure, for the intersection theory or for sort of any of the associators and so on that you'd end up having to write down, there's some sort of distance, and outside of that, it vanishes. So things that are kind of within 5 steps of each other might intersect in some interesting way, but things that are a million steps apart don't interact. That's what I mean by quasi-local. So this is the heart of the talk, is this theorem. Well, half the heart of the left lung of the talk. So let me very quickly, for any of you who are experts in proper ads, tell you why you can do this. The proof is totally by obstruction theory, meaning that you identify, so construct, in general, for any kind of cofibrant, making actions of cofibrant replacements of something, the way you always prove that such a thing exists is you identify what types of obstructions there would be to construct. You try to construct it inductively. At every step, there's some obstruction to doing that. And then you have to prove that that obstruction actually vanishes. So if you tried to do sort of the universal cofibrant replacement, it's too hard. There's just too many generators. But fortunately, this sort of shifted Frobenius guy is Koszul, which if you know what Koszul algebras is, it's the same thing. And if you don't worry about it, which means that I have a much smaller cofibrant replacement if I need it. And for that guy, I can just check that there's only 5 obstructions that have a chance of being non-zero. All the rest, the obstructions live somewhere where I can calculate the homology of there, and it vanishes. And for those 5 obstructions that you have to check by hand, I can check them by hand, and they vanish. Okay, that's the proof. I check something by hand 5 times. And then the rest happens by sort of abstract nonsense. I'll tell you details afterwards if you want. OK, so why is this important? Remember, I wanted to construct a universal star quantization. So I have sort of, as one of the inputs to my problem, I have a Poisson formal manifold. I should really sort of draw some pictures. OK, where is chalk? So I don't know. With the screen's on, is it better to be here or on the sideboards? Here, OK. So to any graph, let's see. So for any directed acyclic graph, gamma, I can associate kind of 2 different things to it. One of the things that you can associate to it, so this is somebody who looks like, and almost like this. Something like that. So I can associate 2 things to it. The first thing I can do is any directed acyclic graph represents a generator in H-Frob, in homotopy Frobenius. Oh, I've totally skipped a slide. Have I? Where was I? No, I'm here. OK, so any directed acyclic graph, kind of, I can do there's sort of 2 things I can associate, 2 pieces of data I can associate to it. The first piece of data I can associate to it is I can associate a generator of homotopy Frobenius, open and one shifted. Sometimes it's the generator called 0 if there's some sort of symmetry that makes it die. And that's just because if you sit down and calculate what homotopy Frobenius is, you realize that it has 1 generator for each graph. Well, or 0 generator. I mean, for every graph, it's either a generator or it's 0. The other thing you can associate to it is you can go through, and I just want you to sort of, you go through and you look at each vertex. And if you ever find a vertex that has like 3 or 1 inputs or something, you kill it. But if it happens to be, so if it happens that every vertex has 2 inputs, if it happens that every vertex has 2 inputs, then you could just decide to put the Poisson, the sort of Taylor coefficient of the Poisson structure at that vertex. So this is not a good example, but maybe that's a good example. So here I'll put like the first Taylor coefficient of the Poisson structure, because I have 1 output. And here I'll put the second Taylor coefficient of the Poisson structure. And here I'll put the second Taylor coefficient. And I hope you can see in the back row. And I can contract these up, and I get some map from some copies of V to copies of V. Whatever, some copies of V to some copies of V, because every Taylor coefficient of the Poisson structure was some map from copies of V to copies of V. So what I'd like you to do, with some coefficients that I won't tell you, but they're easy to describe. It depends on some conventions that you pick. What I'd like you to do is go through all graphs, and for every one, both record the generator in homotopy Frobenius and record the composition in Pois. It's sort of if you think of it as a formal Poisson manifold. Tensor those together. And then what I want you to do is sort of think of the generator in terms of its actions on chains, and think of the Poisson structure in terms of its actions on your Poisson manifold. And this will give you some map from kind of copies. Well, it'll give you some map from copy sort of some number of copies of chains and some number of the same number of copies of your Poisson manifold. And I want you to package all of that data together into the symbol of a differential operator. So that'll give you some sort of differential operator on the completed symmetric algebra of chains valued in your Poisson manifold. And then it's a calculation. Well, it's not that hard, that if you sort of do what's the most natural combinatorial terms, you find out that if you, so you take all of those differential operators. They depend on I want you to also record the number of inputs and the genus. By genus, I mean the first Betti number. So this has genus 1. So you take all those differential operators. You put in a factor of Planck's constant raised to the genus and the number of inputs minus 1, which in this, it's also just the number of vertices, since every graph has every vertex has exactly 2 inputs. And you package all of that data together into one ginormous operator, some sort of pseudo-differential operator. Then the statement is that that operator satisfies a Maurer-Cartan equation. It satisfies a quantum master equation. And this is just some combinatorics of graphs. So what I'd like you to do, so this is, I think, awesome, because what it means that you can do is the following. It means that you can take kind of the completed symmetric algebra of your Poisson formal manifold, and you can take kind of the completed symmetric algebra. What I'd like, I'm just going to draw a picture. You can take the real line, which I've sort of divided up into little intervals. You can pick some point, what did I call it, z maybe? And for any choice of that point, z because he's an integer, for any choice of point that you can pick, you can take some sort of formal power series. So that was some function on the completed on the formal manifold, and you can insert him at that point, iota z of f, just by taking f to kind of well, if he's sort of if he's homogeneous of degree n, you multiply him by n copies of this 0 chain. Anyway, so that's a map from this graded vector space to this graded vector space. And this graded vector space is actually a chain complex, not with just the derivative of chains, but with the chain complex structure twisted by this particular Maurer-Cartan element. I dropped a bracket h bar somewhere. And this is actually a chain map for sort of a stupid reason. This guy's concentrated in degree 0. And when I extend by chains, I only get things in positive degree. And if you have a map from something concentrated in degree 0 to something concentrated in non-negative degrees, it has to be a chain map. But the statement is that this is actually a quasi-isomorphism. Why? Because it would have been a quasi-isomorphism if I didn't have the deformation delta. But the deformation delta is order Planck's constant. And so you have a spectral sequence, and it works out. And you can actually compute everything exactly with the homological perturbation lemma, which you should ask Niels about. One other comment that I should make is that this statement, well, whatever. I won't make that comment. OK, so now I can define the star product. So let me take two different functions. So rather than just having one function, let me take two different ones, f1 and f2. And let me take two different points, z1 and z2. And let me insert f1 at one point and insert f2 at the other point. Then this is some sort of element in, so this, now I get something in the completed symmetric algebra of, so I get some element to z1 of f, who's in the completed symmetric algebra of chains valued in the manifold, and to z2 of f is also in this completed symmetric algebra. And I can multiply them in the completed symmetric algebra. So I have somebody in the completed symmetric algebra. And because I had a quasi-isomorphism here, a quasi-isomorphism from somebody who's concentrated in degree 0 to somebody with positive degrees has a unique left inverse. It's a good exercise. So I have a unique left inverse. You can check that it doesn't depend on where I did the insertion. And so I can apply the unique left inverse. And so I can take the class of this guy, and he represents somebody in the completed symmetric algebra of V. And that's the star product. Well, it's the star product if you take the limit as the 2 points run away from each other. So it's not quite the star product. But for any sort of, this are completed symmetric algebra. So you truncate it anywhere, then eventually as the points get very far apart, then it's a well-defined thing. It's sort of, for any particular truncation, the limit is sort of constant outside of some region by quasi-locality. So the limit makes sense. So the main theorem of the talk is that it's a well-defined associative multiplication. And well-defined is just because sort of the limit is constant. Associative is this picture. And it also OK, that part sort of is formal nonsense. To check the other things, like that this was to check that this is independent of, there were a bunch of obstructions that you had to make vanish to construct the homotopy-Frobenius algebra structure. Independence of that, you have to work a little bit, but it's not, that's actually pretty much formal. But all of the requirements that people normally ask, that like the star product be by bidifferential operators, that actually requires doing a lot of combinatorics of diagrams. How much time do I have left? 5 minutes. Great. OK, so that means I get a minute per slide for the last part, which is fine. So that completed the proof. That's the star product. You can go home and check it. And it's totally defined over the rational numbers. And I never used graphs with directed cycles. So it's even defined for infinite dimensional vector spaces if you ever needed it to be. I mean, I don't know why you would need it to be, but it is. It's defined in any sort of in settings even when you don't have traces, is what I'm saying. So I don't know. Maybe you care about some super something where you don't have traces. I don't know. So let me say kind of where this came from. Should I say where this came from? So this is what's going on is that this is a one-dimensional. It's some version of topological quantum mechanics. Topological because insertion of observables didn't matter. So what is this theory really? This theory is really so this theory is, well, it's a quantization of It's a quantization of the theory of locally constant maps from the real line to whatever your manifold is. So what do I mean by that? And this fits in some general framework that that Dominic Joyce referred to due to AKS and Z. So what do I mean by a quantization? Well, what do I mean by a theory? What I mean by a theory is that I can look at all the maps from R to V star. V star because V means the linear functions on my manifold, so V star is the manifold itself. And then the manifold V star is Poisson, and if you look at mapping spaces into a Poisson manifold, it's not Poisson, it's hopeless. But you can still construct homotopy Poisson structures. And that has to do with some sort of tree-level version of what I just told you. Those are called dioperades. I don't know why. And then by quantization, what I mean is that so this mapping space turns out to, you can construct on it a homotopy Poisson structure where the Poisson bracket has degree -1. And then you sort of remember maybe that sort of for any problem of actually computing path integrals, you maybe read Kevin's book or something like that, and you find out that for any problem that has to do with computing path integrals, there's a complex, which is an algebra with a degree -1 Poisson bracket on it. And the problem of defining a measure and doing computations is the same as the problem of solving a Maurer-Cartan equation that starts with that degree -1 Poisson bracket. So that's what I mean by quantization. A quantization is a solution to a Maurer-Cartan equation that to leading order is the Poisson bracket that you have. Well, anyway, so if there are experts here, I wanted to just say once again that kind of having a homotopy one-shifted Poisson structure by definition is an algebra for the dioperad, which is the bar construction of zero-shifted Frobenius open. And to have a quantization of it is to lift that to a properatic thing. Dioperad means tree level, properatic means graph level, and that's all they mean. So this is the same properad that Kenji Fukaya called the involutive Lie by infinity, something like that. I don't have time, so you should talk to Kevin about how this fits into factorization algebras. And I'll just end by saying that this really is a thing about field theory. We have this really is a field theory where the classical fields are cochains valued in the manifold. Cochains because I want to resolve the notion of locally constant, and when somehow the thing that resolves locally constant is cochains. So the algebra of observables would be, the linear observables would be chains valued in the vector space V. And the whole point of sort of one of the messages I want to make to you is that the notion that when you do this sort of derived field theory stuff, you should feel very free to choose any convenient model of cochains or chains that you want. Classically, people have always used Durham cochains or Durham chains. Durham chains meaning like compactly supported distributional Durham forms. But you don't have to. I'm using cellular chains. Renormalization schemes should not, I thought they were very scary for a while until I realized that they're just the problem that multiplication isn't associative at the chain level, intersection isn't associative. And the renormalization scheme is the choice of how to extend some naive intersection theory of chains to a homotopy Frobenius algebra structure. I'm working on a lattice, so my only observables are sort of supported on the sort of cells of my lattice. So my only fields are like constant on the lattice. And so I already had some sum of graphs a while back. There it is. That sum of graphs just is sort of doing the path integral down to an effective action that just lives on the lattice. The star product is just the endpoint function that you're used to. And the final sort of hidden somewhere in there was a lot of application of homological perturbation lemma and a lot of explicit formulas. And those have a lot of sums and can be written in terms of sums of diagrams as well. And that's sort of computing the final path integral. So thank you for listening, and I'll stop here.
Including the extra conditions that allows you to use like the formal geometry included together.
So one of the things that people call universal star products has to do with sort of macroscopic manifolds, and has to do, as you say, with gluing together different coordinate patches. And I don't know if this glues together. I just haven't calculated how my thing transforms under changes of coordinates. I have never done a computation in formal geometry, and in sort of the stuff that you're referring to. So that would be an interesting thing to look at. My construction is only in one infinitesimal neighborhood with a choice of affine chart in that neighborhood.
What happens in higher dimensions?
That's a good question. In general, what you'd need to make a similar machine work in higher dimensions. So for the dioparad level, I can do everything, as long as I'm on an oriented manifold. Well, OK. I can do everything modulo some problem in topology that I'm sure that any good topologist can solve. I mean, it must be true. At the properad level, it's harder. I needed the causality of some properad to make the, so what I need, so the universal cofibrant replacement at the properadic level is too big to be useful for constructions. So you need a much smaller cofibrant replacement. So in dimension 1, the cofibrant replacement that comes from causal duality wins the day. In even dimensions, shifted Frobenius is not known to be causal, so you don't even have it. And in any case, even if it were, the one that comes from causal duality is still too big. It has too many generators where the obstructions don't vanish. So what I can do is since I have it for R, I can multiply it with itself, and I can do everything kind of on Rn, but on framed Rn. I mean, I can't do it kind of except for framed Rn and, quotients of it by a lattice. So with Owen Gwilliam, we're going to look at doing this in dimension 2, where we hope to be able to do the two-dimensional version so there's a sequence of quantization problems that in dimension 1 is universal star quantization of Poisson manifolds. In dimension 2 is Eddinghoff-Kazhdan by quantization. And we think we know how to do the same thing there. In dimension 3, it's constructing Chern-Simons theory, and I don't know how to do that. But I presumably could do something that would construct like Chern-Simons theory in the 3 torus. And that would be all I could do. This really breaks kind of because there's too many. The cofibrant replacements are still too large.